So the first theorem says that if a function is differentiable at a point, then it is continuous at that point. Something that will help in addition to this one is that if all the first order partials of a function f, let's say, exist and are continuous at a point, then f is differentiable at that point. Bless you.
Thanks.
So as far as figuring out whether a function is differentiable everywhere, so for a quick example, let's say we have a three-variable function f of x, y, z. Let's say we have that it's x plus y, z. Okay, kind of using the second one. If we find the first order partials, so f sub x, f sub y, f sub z, which in this case would be what?
1.
Good. What do we know about the function 1, the function z, and the function y? These are all continuous, and not just at a point, but everywhere. Which then, therefore, means that f is differentiable everywhere as well. So, if you recall the last example we did before the end of class yesterday where it said prove that this function is differentiable everywhere, now you have two options. Okay? Unless I say to specifically use the definition of differentiability, this is probably the easiest way to do it. Does that make sense? Just take the first order partials and say, oh look, these are all continuous everywhere, so that means that the original function is differentiable everywhere too. Okay? Questions on that? Let's close that door over there. Thanks. All right, so now we're going to touch a bit on differentials. So let's start with dz. The total differential of z is defined as, I don't know why I switched colors, sorry, partial x evaluated at a point dx plus partial y evaluated at the point dy, which is very similar to the formula we talked about yesterday, which was an approximation. We call this the total differential of z. Yesterday we had a formula that looked like this. What's that?
What's the difference?
The difference is that this is more of an exact equation. The other one's an approximation. Which we had, I think it was change in f was approximately equal to partial x delta x. plus partial y delta y.
Those look like the same.
They pretty much are. The only difference is that here we're actually using delta x instead of dx. Okay, and when we start doing differential equations, I mean, it'll make more sense a little bit. Okay, so here's what we need to, just with the notation. If you can follow the notation, okay, just keep track of this is the actual change, which is approximated by this formula. Okay. However, we can use the total differential, so like dz will help us approximate the real change. When we do an example, this will get cleared up. Okay, so when we use the notation delta z, that actually means the difference in the, if you think of a three-variable or a three-dimensional function, it actually represents the changes in height, okay, at a specific point. And then this formula here will help us approximate what that change looks like. Okay? So here's what it looks like in context now. Let's say we have the function z equals xy squared. And we want to do a couple of things. One, we want to approximate the change in z from the point 0.5 to 1.0 for y. If we start there and move to, let's say, 0.503 to 1.004. If you have calculators, you're going to probably use them a little bit here. Okay. So let's find the total differential. That's what we do first, which was partial x. So in this case, partial x is y squared dx plus partial y, which will be 2xy dy. And we're going to be dealing a lot with this kind of thing in diffie-q, but for now we'll just treat it the way it is. So this is our total differential. Okay? Now, we're going to treat dx as the change in x, and we're going to treat dy as the change in y. So now we're going to approximate the change. So then dz, using, just to make this clearer, this is our initial point, and this is where we are moving to, okay? So what is the value of y at this initial point? So it would be 1 squared. And now we're going to treat this as change in x. So from 1.004 back to 1.0 changes. Oh no, I'm looking at the y, sorry. From 0.503 to 0.5, the change was 0.003 plus 2. Now we plug in the x and y coordinates, so 0.5, 1.0, and then the change in y is 0.004. Change, right, because we started at 1. Okay. So yeah, type this in. What do we get? 0.007? Okay. So this is the approximate change. In Z. Okay? So if we're at this point, we move a little bit away from it, we've increased our height by 0.007, approximately. Bless you. Okay, so now the second thing that we'll do is actually compare the approximate change to the real change and see what kind of error we have in comparison to the distance between the original points. So I think the directions will say something like find magnitude of error and compare to the distance between, let's say, well, we're going to use the same point. So 0.5, 1.0 to 0.503 to 1.004. Okay, so the first thing we're going to do is now we'll compute delta Z, which is the actual change in Z. Okay? So at the point 0.5, whoops, I don't know why I closed the parentheses, 0.5, 1.0, what does Z equal? .5. Okay. Now, if we go to the point 0.503, 1.004, now we get another output. What is that? 0.50. Let's get a lot of decimals because we're going to compare this. 0.032. Okay. Good enough.
What were you expecting?
Well, because if we say 0.507 and then our approximation is that it's 0.007, then what we have is a perfect, right? We know it's not. Okay, so we want to go a little deeper and get some more after that. Okay, so now the change in Z, which again, this is the real change in Z, right? Is going to be, if you subtract the value at 0.503, 1.004, and then minus the original value, 0.007032048, and so on. Okay. So now the error will be the absolute value of the approximation minus the real change. Help me out. I guess I don't. It's just point. Well, we're going to divide by the length in a minute here. Let's see. The 0.007s drop out, so 0.000. Is that right?
Yes.
32048. So there's the error in our approximation. Bless you. Okay, so now here's what this means when I say find the magnitude of error and compare to the distance between these 2 points. So what's the distance between those 2 points? 0.005. Okay. So if you use distance formula, or maybe you just see the triple there, the distance between this point to that point is 0.005. So what we do is say 0.000032048 divided by this distance is approximately. So now we're finding the magnitude and error compared to the distance between the 2 points. 0.00640.
9.
Okay. So let's just leave it there.
0.9.
Okay. So this is good. I think the book likes you like saying finding a fraction that's a little bigger than it. Like they'll say that this is less than
DZ.
now let's see. If I did, let's think of a fraction that's a little bigger. Can you guys find a fraction for 0.00641? Convert it to a fraction. What is that? 65 10 thousandths.
How the hell you figure this?
Does it reduce? 13 over 200. So it's less than 13 200ths. 2000. 13 over 2000 of the distance
What do we?
between the 2 points.
Do you have to do that?
Look, I honestly don't care.
What's the point?
I'm just letting you know that this is, if you see like in the answer that they have this, oh, the distance or the magnitude in air is less than 1/1000th of the distance. It's like, what do they talk? This is how they're getting all that. Okay, if I ask this for you on an exam, honestly,
You would.
I might just say, tell me the error. I wouldn't really care about, you know what I mean? So like that would probably be good for me. Okay?
Could we make it complicated too, like a regular fraction?
Sure, if you wanted to. Okay. Length, the length, width, height of it. I don't think we need to do that. Maybe we'll go back to it if we have time. Okay. Let's get to the last topic then. So we know the definition for differentiability from yesterday. We know how to find if the function is differentiable. We have two options now, right? Either use the definition, which sucks, sorry, or use the theorems that we talked about earlier, right? Compute differentials, we can do that. Now we know how to use these differentials to approximate change. The last thing is to look for local linear approximations. Let's take a look at that. Okay, local linear approximation. If f is differentiable, and can be closely approximated That's not what I meant. If f is differentiable, not and, it. If f is differentiable, it can be closely approximated by a linear function near that point. And it looks something like this. L of xy will equal and hopefully this makes sense to you. Initial point evaluated plus partial x evaluated at initial point times change in x plus partial y evaluated at initial point times change in y. So, look, it's not that hard. These are the new coordinates, if you want. These are the new coordinates. This represents what? The original value. And this is another way to approximate the change, right? So if we have an initial point like 1, 2, and now we're looking at 1.1, 2.1, we can use this linear equation to figure out what that exact output is. Okay, so here's an example. Let's say f of xy equals the square root of x squared plus y squared at the point 3, 4. So this is where we're at, sorry. Let's find a local linear approximation. So that'll be the first thing. Okay, so if I were asking this on an exam or in the homework, you should have a function, L of xy equals, and then like an actual equation where you just plug everything into, so that you could approximate several different points that are near that value. Okay? So what do we need? We first need to find what? Yeah. So what is f of 3, 4? Next, we should find partial x. Partial x will be x over something Carl mumbled.
Yeah.
Which sounds like that, I'm assuming? Okay. Partial y will be?
Y over the same thing.
Yep. So now, at 3, 4, what does this turn into? 3/5. And this at 3, 4, since that's our original point, equals 4/5. So now our function, L of xy, is going to be initial point, which is 5, plus this entire thing we've just figured out, right? All of that is 3/5. And then now we have what? X minus 3 plus 4/5. Yep, y minus 4. Okay, so this is your local linear approximation. This will approximate any coordinate, any z value, as long as the coordinate is near the point 3, 4. So why don't you guys do this one? Let's approximate, use L to approximate f at the point 3.04 and 3.98. What are we getting?
5.08.
Everybody on the same page? Okay. So there's our approximate output. C. Compare error with distance between the 2 points. So that's kind of like what we did earlier, but we can just get to that decimal. So find that proportion. or that ratio. So, how do we find the error? The error is going to equal
Difference over the distance.
the actual, the difference in the real change, right, minus the approximate change, which now we have that function L of 3.04, 3.98. I'll do the hard part. 5.008. Can someone help us out and find the actual change in f? Well, I guess this notation is horrible. Anyway, hold on.
Wait, why?
Because I said change in f, but we're actually, I'll explain in a minute. 5.0081, what did you say?
93287.
Okay. Let's just cross that out, because that doesn't make sense. This,
Why does that not make sense?
because the actual change in f, if we start at f5, is what?
Oh, so we get
0.0, you see what I'm saying?
I see.
I just messed the notation up. The approximate change was 0.008, right? Because we have this approximation, subtract 5. So there's our approximate change. So then the error is approximately, if you take the difference here, 0.00193287. And if we compare that to the distance, so the magnitude in error will be that divided by the distance between the 2 points. That's not a nice triple, but it'll be calculated by doing the square root of, what was the change there? 0.04 plus 0.02 squared.
Mhm.
So then we get something like
0. Oh wait, no, that's just the number.
0.004322.
okay, good enough. So about 0.43%. Is that what everybody else is getting to? Okay. Okay. That last example would take. You know what? Do you guys have questions you want to go over from homework since we have some time before class is over?